So this is Notes Part 3, Chapter 12, and we're going to be talking about real and ideal gases and the ideal gas law. So the bell work was completing a couple of statements. When the pressure of a gas goes up, the volume actually decreases, and this is called an indirect relationship. One goes up, the pressure goes up, and one goes down. That's indirect. So when the temperature of a gas goes up, the volume will also increase, and we call this a direct relationship. When the temperature of a gas goes up, the pressure also goes up, and again, this is called a direct relationship. So an ideal gas follows gas laws and conditions of temperature and pressure. So ideal gases, that's what we think about. And that's what the three laws we've used, Boyle's, Charles, and Lusak's law, that was in the last video. But actually, those types of gases don't exist. We have real gases, and real gases can be liquefied and sometimes solidified. The ideal gases that we've been talked about, they really can't. With the equations that we have, we could decrease the temperature as low as we wanted to, and it would still be considered a gas, and that just doesn't happen in real life. Gases behave most ideally at temperatures that are high and low pressure, and we like to think about this like us in the summertime. There's not a whole lot of pressure, we're not in school, and we have high temperatures. So gases behave and follow those laws, Boyle's, Charles, and Lusak's, more ideally at those conditions. The ideal gas law here allows us to include the amount of gas in our calculations. Previously, with Boyle's, Charles, Lusak's, the amount of gas has stayed constant, and that's why we didn't see it. Here, we're going to be looking at an equation that focuses on the same conditions, but we want to know one thing about the gas, whether it's pressure, whether it's volume, whether it's the number of moles or the amount of gas, and whether it's temperature. This ideal gas constant here, there's a bunch of different values for it, but this one that we focus on has volume in liters, has pressure in atm, amount of gas in moles, and then the temperature is in Kelvin, which we've already been doing, but we're going to continue to do that. A way that we kind of remember this here, we say PUVNERT, and it's a good way to remember that PV equals nRT. So here's an example using the ideal gas law. 5-liter flask contains 0.6 grams of O2 at a temperature of 22 degrees Celsius. What is the pressure in atms inside the flask? Well, they give us here a volume in liters. They give us an amount of gas in grams, and eventually we're going to be putting that into moles, so that's our N, and then a temperature here of 22 degrees Celsius. We want to know what the pressure is. So if we go through it, we don't know the pressure. We want to figure that out. The volume is 5. Our gas constant will be included here, and we know that that is constant, and it's always given to us. The number could change, but in this case, we're always going to use 0.0821 in this unit. Temperature is 22 degrees. We want to put that into Kelvin, so we're going to do that right there. So here we go. This is a refresher. We are taking the amount of oxygen gas and putting it into moles using this conversion factor, which we call molar mass. It can also be called GFM for gram formula mass. But anyway, oxygen on the periodic table has a mass of 15.999. And since there are 2 oxygen molecules, we're going to go ahead and bump that up to 32. It's like saying 16 times 2. And that value, of course, goes right here. That is how many grams per mole of O2 there is. And we finally get our amount in moles, which is what we want. So if we use the ideal gas equation right here, we're just going to take the numbers that we have and plug them in. So here's our volume, here is our N, R, and T. and the P, of course, we don't know. We need to solve for it. And after we do, we get 0.091 ATMs. Another example of the ideal gas, how many grams of krypton are present in a 600 milliliter container? And this should actually look like milliliters with a little m, big L, at 1010 degrees Celsius, 1010 degrees Celsius, in which the pressure of krypton is 10 atm. Well, down at the bottom right, we have the element krypton. It's a heavy, heavy, noble gas in group 18. So we're going to look at it in the sense of the ideal gas equation and figure out what the pressure is going to be. Or excuse me, we're looking for how many grams there are. So I'm going to pick apart my problem here. I want to know how many grams there are. I'm given a volume, I'm given a temperature, and I'm given a pressure here. So let's go through it. P is 10 ATM. In the ideal gas equation, we want pressure in ATM, so we're good there. Here, the volume is in milliliters, but we wanted it, for the sake of our R constant, in liters, so we had to divide by 1,000 here. In, we don't know, we're going to figure that out. R is always given at those different units, liters, ATM, moles, and Kelvin. Temperature here, 1010, always put it into Kelvin, always. Okay, and after you do that, you get a temperature in Kelvin, which is what we want. And again, we're doing this so that we get liters, we get ATMs, moles, and Kelvin, so that our R constant is the correct value. It's basically the glue that keeps this together. So here's our equation, PV equals nRT. 10 ATMs is our pressure that we're plugging in. Here's the pressure, the volume, in we're looking for RT is there. So after we solve, we are going to get a number that is in moles. And we get 0.05696 moles of krypton. Okay, so if we want to put this into grams, because that's what we're looking for in the problem up here, we are looking for grams. So what we have to do is take this and use our mole to grams ratio. We used a molar mass ratio before. In this case, it's flipped so that our units here, moles, can cancel out. So we looked on the periodic table and got the molar mass of krypton, and it's not Kr2, it's just Kr, so we took that value and plugged it in here. You multiply those two numbers and you get a value of 4.77 grams. In certain problems, they may ask you to take it a step further and use prior knowledge from previous topics. And they may say, well, you got the grams, but how many atoms is that? Well, let's just use some previous knowledge and go through it. So we remember that if we are in moles, we can go to grams using molar mass. And again, this is moles. And if we want to go to atoms, okay, if we want to go to atoms, we use the value 6.02 times 10 to the 23rd. And then if we wanted to go to volume, we would use 22.4 liters. So that's what we use here. Our conversion factor, we're in moles, and we want to go to atoms. We will use this number, Avogadro's number, 6.02 times 10 to the 23rd. You multiply those two, and you get 3.43 times 10 to the 22 atoms of krypton. So the next topic, we're going to talk a little bit about gas molecules as far as mixtures and how they move. And we're going to see a couple of different laws here. Avogadro's hypothesis says that equal volumes of gases at the same temperature and pressure have equal number of particles. So at STP, the temperature is 0 degrees Celsius and 1 ATM. So what Avogadro had stated was that if you have the same conditions, if you have 1 ATM of pressure and 0 degrees Celsius, no matter what type of gas that you have, you're going to have the same number of gas particles floating around. And so down below at STP, 1 mole is 22.4 liters. Well, that's not new information. We've seen this before, but Avogadro's hypothesis is how this number came about. We have Dalton's law of partial pressure, which states that at a constant volume and temperature, the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures. So this got a puffy cloud of greatness, and what it says is that the total amount of gas, so if you have a container here that contains several different gases, in this case we have helium and hydrogen, that total pressure is going to equal the pressure of hydrogen and the pressure of helium put together. You're going to get your P total. So here's an example of Dalton's partial pressure law. Determine the total pressure of a gas mixture that contains nitrogen and oxygen if the partial pressure of the nitrogen is 725 millimeters mercury and the partial pressure of oxygen is 426 millimeters mercury. So a good part again is to pick apart the problem. You have two gases. You have nitrogen and you have oxygen. Well, if the partial pressure of nitrogen is 725 millimeters mercury and the partial pressure of oxygen is 426 millimeters mercury, we would be using partial pressure law to add up both of these pressures. If you add, and real quick, this pressure 1 might be like nitrogen, and then this pressure 2 could be the oxygen gas. Okay, so you're adding these two pressures up, and you're going to get a total of 1151 millimeters Hg. Straightforward problem, but you got to be careful. Make sure that you're adding up the gases in the container. Gases are often collected by water displacement. The total of the gas pressure plus the water vapor pressure is equal to the atmospheric pressure. So when we work a problem like this, we must always look up and subtract the water vapor pressure to get the gas pressure. So in this picture, a common way to collect gases is using an inverted bottle. And what we're looking at here is all around us, all in here, you have the atmospheric pressure. And then down here that's coming off the water, you're going to have a water vapor pressure. And then inside this container, you're going to have pressure from the gas inside. So that's going to be your gas pressure. And so there's going to be a problem that mentions atmospheric pressure, one that mentions water vapor. And so what you have to do is subtract away the water vapor from the atmospheric pressure that is all around in order to get the pressure of just this container inside here. So let's look at an example. So sample of N2 gas is collected by the downward displacement of water from an inverted bottle. That's what that picture looked like on the last slide. What is the partial pressure of the nitrogen gas at 20 degrees Celsius if the atmospheric pressure is 752 millimeters mercury? The water vapor pressure is 17.5 millimeter mercury at 20 degrees Celsius. Here in this problem, the temperature is constant, so we will not be using this value because it doesn't change. So let's look at our equation. Dalton's law of partial pressure looks more like this. P1 plus P2 equals P total. In this case, when we are dealing with a problem that mentions water vapor pressure or atmospheric pressure, okay, and also a pressure of a gas, it's going to look more like this, where we have the water vapor pressure here, and we have the total pressure, which is the atmospheric pressure here. So that's a good thing to note. And this would be the water vapor pressure. And then, of course, we're looking for the pressure of nitrogen gas. So we would plug in the values for water vapor pressure at 17.5 millimeters mercury and the total atmospheric pressure of 752 millimeter mercury. And then we would solve by subtracting 17.5 on both sides and getting a value of 735 millimeter mercury for the pressure of nitrogen inside that bottle. With scuba, if you've ever gone scuba diving, it's awesome, and there's some awesome chemistry behind the gases and the gas laws. And so, personally, I've never been scuba diving, but scuba stands for self-contained underwater breathing apparatus, and it uses a pressurized tank in order to help you survive at extremely high pressures underwater. At the surface, you're swimming at a pressure of 1 atm, and we know that pressure as the standard pressure. If you dive down 10 meters, you're going to increase 1 atmosphere each time you do that. So, for example, at 30 meters, the pressure bumps up to 4 atms. At 40 meters, you get to a pressure of 5 atms, and at that pressure, you're not actually physically strong enough to inflate the lungs on your own. And so this is what scuba gear does. What it does is it uses that pressurized air inside that tank to force air into your lungs so that you can breathe normally. If you ascend, which means if you go up without exhaling or without breathing out, when you ascend to the surface, the gas inside your lungs begin to expand. Just like when you go up to a high mountain, there's less pressure there, and so gases tend to expand. And so if you ascend from a deep depth during scuba diving without exhaling, then you have the possibility of rupturing a lung, which is very dangerous. Okay, so it follows the gas laws, but it also affects your health. So if you go from 40 meters to the surface, the volume inside of your lungs could increase 5-fold, which is not good. So if you ascend, you're going to be constantly exhaling because that gas is expanding. There's another condition called the bends, where the nitrogen compounds in your blood will dissolve because of the high pressures. When you're down low into the ocean or wherever you're diving, that pressure will force gas molecules to dissolve. So that's what this picture is showing here, that when you increase pressure, you can dissolve more of these gas molecules into a liquid. In this case, it's your blood. If you go back up to the surface too quickly, this nitrogen will come back out of your blood in the form of bubbles, and you will experience chronic pain, joint pain, and in serious cases, death. So if you are a long-time scuba diver, chances are that you have some joint pain and chronic health effects from what we call the bends.